Have you ever stopped to think about how the simple math we all learned as kids can, well, scale up? How a basic idea like equals can transform into a tool so powerful it can describe the entire universe and pose riddles that stump the greatest minds for centuries. It's kind of a wild thought, right? So let's do it. Let's take that exact journey from simple sums to universal truths. Everything, and I mean everything, kicks off with a question that sounds almost too simple. What does it actually mean for two things to be the same? Now, we use this concept every day without a second thought. But in the world of math and logic, sameness has a very, very precise and powerful meaning.
And our first real clue comes from way back in elementary school. We learned that something like 5 plus 2 and 9 minus 2, well, they don't look the same at all, do they? But they're the same in a much deeper sense. They share the same value. They're both just 7. And there's a special word for this, equivalent. That one little idea is the seed from which this entire tree of logic grows.
Okay, so if things can look different on the surface but be the same underneath, we need a way to talk about how they're the same. And it turns out the best way to do this is to think about it like you're wearing two different hats, one for doing arithmetic and one for thinking with logic. So let's try these hats on. When we're wearing our arithmetic hat, it's pretty straightforward. We look at 5 plus 2 and 9 minus 2. Yep, they look different, but we crunch the numbers and boom, they both have the same value, 7. Easy. But now, let's switch to our logic hat. Here, we deal with statements, not numbers. So P and Q looks different from Q and P. Instead of calculating a value, we check their truth. We can map out every possibility in something called a truth table. And when we do that, we find that P and Q and P are true and false under the exact same conditions. Their truth tables are a perfect match.
And that, right there, is the big idea. This is called logical equivalence, and it is the absolute bedrock of all reasoning. It's just like knowing that x times y is always the same as y times x. It's a fundamental rule that lets you rearrange and simplify an argument with total confidence, knowing you haven't broken the underlying logic.
So, with this powerful idea of equivalence in our pocket, we can start to build. We're going to move from just comparing statements to actually constructing arguments. And the single most important building block, the Lego brick for basically any argument, is the if-then statement.
Here's a classic. We hear and use this kind of thinking all the time. It's called an implication. It connects two ideas together, but it's a one-way street. If the first part is true, it forces the second part to be true. It's simple, it's intuitive, and it is the engine that drives all logical deduction.
Now here's where logic has a little quirk that's actually fascinating. An if-then statement is only considered false in one very specific situation, when the if part is true, but the then part turns out to be false. Think of it like a promise. If I say, if it's raining, I'll bring an umbrella. The only way I've lied to you is if it does rain and I show up with no umbrella. If it doesn't rain, my promise is safe, whether I have an umbrella or not. It's a really clever way to define truth. Okay, and this is where so many arguments go wrong in the real world. You can shuffle around an if-then statement, but not all rearrangements are created equal. Our original statement is, if it rains, the sidewalk is wet. Simple enough. Now let's try flipping it. That's called the converse. If the sidewalk is wet, then it's raining. Is that always true? Of course not. The sprinklers could be on. So the converse is not equivalent. But now check out the contrapositive. If the sidewalk is not wet, then it is not raining. Now that is 100% solid. It means the exact same thing as our original statement. They are logically equivalent. Understanding this difference is like a superpower for spotting faulty reasoning. Let's ground this with probably the most famous theorem in all of math. The Pythagorean theorem is a perfect implication. The if part is you have a right triangle. The then part is that famous formula. And this is a perfect example of what we were just talking about. The converse of the theorem, flipping it to say, if the formula works, then it's a right triangle, is a completely separate statement. It is not automatically true just because the original is. Now, in this very special case, mathematicians went ahead and proved that the converse is also true, but it had to be proven separately. A statement and its converse are two different logical beasts. All right, so we've got our building blocks, equivalence and implication. Now we're going to add the turbochargers. We're about to introduce a couple of tools that let us apply this logic not just to single one-off statements, but to entire groups of things, even an infinite number of things.
And these are our tools. They're called quantifiers. That upside-down A is the universal quantifier. It just means for all or for every.
It lets us make huge, sweeping claims like all stars are massive balls of gas. Then there's the backward E, the existential quantifier. This one just means there exists, or there is at least one. It's how we claim something is out there, like there exists a planet made of diamonds.
And with just these two new symbols, we officially graduate to something called predicate logic. This is where logic stops being a classroom exercise and becomes an incredibly powerful tool for describing the real world. We can now make precise, testable claims about entire categories of things.
So what can we really do with this new high-powered language? Well, we can use it to state some of the most profound, most difficult questions humanity has ever wrestled with. We can write down riddles that are so perfectly clear there's no ambiguity at all, only an immense, challenging search for the answer.
Take a look at Goldbach's conjecture from way back in 1742. The idea is simple. 4 is 2 plus 2. 6 is 3 plus 3. 8 is 3 plus 5. 10 is 5 plus 5. It seems to work every single time you try it. But the question is, does it work for all of them, forever, out to infinity?
And here it is, written in the language you now understand. For all integers n greater than or equal to 2, there exists a prime p and a prime q such that 2n equals p plus q. That entire centuries-old mystery captured in one perfectly clean line of logic. And guess what? To this day, nobody has been able to prove or disprove it.
Or how about this one, an even older riddle from 1637? A mathematician named Pierre de Fermat claimed that while you can make x squared plus y squared equals z squared work with whole numbers, you can never do it if you change that power to 3, or 4, or 5, or anything higher. He famously wrote in the margin of a book that he had a truly remarkable proof, but the margin was too small to fit it.
And there it is in predicate logic. That statement says with absolute precision, for any integer n bigger than 2, there does not exist a set of positive whole numbers x, y, and z that solves the equation. It is an unbelievably compact and powerful way to state a gigantic idea that covers all numbers forever.
Now, unlike Goldbach's conjecture, this story has an ending. After literally centuries of the world's most brilliant minds trying and failing to find a proof, a mathematician named Andrew Wiles finally published a complete and correct one in 1994. The perfectly clear question, posed in the language of logic all those years ago, finally had its answer.
This whole journey, from something as simple as equivalence to these massive theorems, really shows you something. Logic isn't just a way to check your work. It's a creative language for asking the deepest, most difficult questions we can possibly imagine.
357 years. Just let that sink in for a second. That's how long Fermat's perfectly stated riddle stood as a challenge to the world. Logic gave us the language to pose a perfect, unambiguous question, but it took centuries of human ingenuity and the creation of entirely new fields of mathematics just to build a bridge to the solution.
So what started with a simple idea about 5 plus 2 being the same as 9 minus 2 has scaled up into a language powerful enough to frame questions that can define the work of generations. The only real question left is, of all these perfectly stated riddles still out there, which one will we solve next?